Hello, Bacho, and welcome to the world of chemistry. So today we are going to learn a very interesting topic from chemistry, class 11, that is periodicity and classification of elements. So this is very important topic, very small topic, but there are so many concepts in that. So many exceptions are there. So we have to focus, we have to study this topic very thoroughly, and then we'll be able to understand it nicely. Okay, so let's start with concept from periodic table, that is ionization enthalpy. This is some trends in period, like periodicity means some trends. So some trends in periodicity, that one of the trend is ionization enthalpy. Okay, so let's see ionization enthalpy. So what is meant by ionization enthalpy? First of all, we should know what is ionization enthalpy. Enthalpy. What is enthalpy? Basically, enthalpy is energy, we can say, because some before some enthalpy was there, after some enthalpy. So there is some change in enthalpy. So that change means some energy. So ionization enthalpy means energy. So let's see what is ionization enthalpy and its exceptions. So ionization enthalpy. Ionization enthalpy. So what is ionization enthalpy? The energy. The energy the energy required to remove an electron from a gaseous atom. What is ionization enthalpy? Ionization enthalpy is the energy required to remove an electron, or in more, if you say, it is valence electron. The energy required to remove an valence electron from a gaseous atom. Gaseous atom. So this is ionization enthalpy. Why we have used a gaseous atom? So atoms are in gaseous state? No, many atoms are there in solid state, liquid state. Like metals are in gaseous, solid state, and non-metals. Most of the non-metals are gaseous. But is that mean that ionization enthalpy is for gaseous only and no for not for metals? No. Here it is mentioned ionization enthalpy means for gaseous atom. Gaseous atom, why? Because it is very difficult to remove an electron from a metal or like solid. So we have to convert solid into gases first of all, and then we can remove an electron. Got it? So that for removing. So see, here is one atom, M atom, and some shells, Bohr's atomic orbital. Some shells are there, orbitals. So here is the electron, and we have to remove that electron. What we have to do? We have to remove that electron. So what we are doing here, we are providing some energy. So if some boys or some students are like they are sitting, and they are like they have made the chain circle. So we have to pull one from outside, like we have to remove one from that chain. Then what we have to do? We have to give some energy from outside. Okay, so here we are providing some energy. So here we are giving energy. So energy required here, what is happening? Energy is required from outside. That you should fix in your mind. Energy is required. Energy is required from outside. So energy is required to remove an electron from an gaseous atom. So that is ionization enthalpy. Got it? Ionization enthalpy. So some trends in ionization enthalpy. Okay. Some trends. What is trends? Periodic trends means, like, first we study about atomic radius. If you know atomic radius, so atomic radius from left to right. If you are going from left to right, then atomic radius decreases. Why? Because Z effect increases. Like that, there is some trends in ionization enthalpy as well. So what is the trends? As size decreases, see, as size is decreasing. Why is decreasing? Because of effective nuclear charge increasing. So if size gets decrease, then it becomes very difficult to remove an electron. See, this is nucleus and this is an orbital. Here is electron. So some force, electrostatic force of attraction is there between two electrons. So we know this electrostatic force is inversely proportional to the distance. As distance increases, electrostatic force decreases. So as distance increases, see, from left to right, if you are going from left to right in the periodic table, what happens? Size decreases. So size is decreasing. Size is decreasing means what is happening? The distance is decreasing. And I said the distance, electrostatic force of attraction is inversely proportional to the distance, the radius. So inversely proportional to if the radius is low, then the electrostatic force of attraction is more. That means nucleus is pulling so hard that it is very difficult to remove an electron from that atom, particular atom. So that means from left to right, if you go in the periodic table, if you go from left to right, size is decreasing. Then what is happening? Size is decreasing means ionization enthalpy increasing. Ionization enthalpy increasing. But there are some exceptions in that. Actually, basically, you need to understand what is ionization enthalpy. We have to remove an electron. So the if that electron is more stable than like some other elements, then it is very difficult to remove. So stability is the factor which decides the ionization enthalpy. And who decides the stability? That is electronic configuration. So if you know the electronic configuration of the atom, then it is very easy to understand the ionization enthalpy. So let's see what is the exceptions. What are exceptions in periodic table or ionization enthalpy? Yeah. So first, from left to right, if you take the second period elements, then lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. So expected trend. What is the expected trend? So expected, yeah, expected trend in ionization enthalpy, IE. So what is the expected trend? Expected trend is lithium less than, beryllium less than this. So this is expected trend, but actually what observed? So what is observed? Some exceptions, some different thing, like lithium, then came boron, then beryllium, then carbon, then came oxygen, then nitrogen and fluorine. So here is these two exceptions, this boron, beryllium, and oxygen, nitrogen. So what is the exception? The nitrogen should have less ionization enthalpy than oxygen, but what is happening here? The nitrogen is having more ionization enthalpy. We have observed that. And in case of boron, the same thing. So why is this happening? Why this thing is exception having a logic like if you say oh exception, so that does that mean it's illogical? No, there is logic, there is concept behind it. So that's why I'm telling you, you should know the electronic configuration. So what is the electronic configuration of beryllium? So if we, yeah, beryllium atomic number 4. So 1s2, 2s2. And for boron, it is 1s2, 2s2, and 2p1. See, so it is easy to remove this p electron because it is unpaired electron. But it is very difficult to remove this 2s electron because it is in pairing, it is paired. We know this s orbital is this like this, and p contains 3 orbitals and this 1 electron. So the whole orbital, only one person is living. See, some like in whole like home big, there is a big bungalow and only one person is living. So if you just call, hello, can you come for the, can you come, yeah, can you come with me? I'm going for movie or something like that. And that person will say, oh yeah, hooray, yeah, I'll come immediately. So why? Because you need very little energy to like call that person. Very little energy. Just you call. But there is one room and two persons are living. Very good friend. They are playing PUBG or they are playing some games. And if you call them, I'm going for movie, they will go. Then go. They will say, yeah, you can go. What does that mean? That means you will need more energy to remove and one electron. You have to tell, okay, I'll pay the ticket, I'll pay for your ticket, you come, just come for me, because nobody's coming with me. So you have to pay. That means you need extra energy. Like that, beryllium needs extra energy. That's why beryllium has more energy enthalpy than boron. It's clear. And next is nitrogen and oxygen. So why nitrogen is having more energy enthalpy? Because if you see the nitrogen electronic configuration, then it is valence electronic configuration 2s2 and 2p3. So 2s2 means this two electrons, and 2p3 we know by Hund's rule this we have to put the electrons in one orbit, because pairing needs more energy than unpairing, because this concept you will learn more in atomic structure and coordination compound, the pairing and unpairing, that will discuss after like after some time. But you need to focus this. See what is happening there. This this 2p3 means this is half filled, you can see this is half filled. And we know that if the orbital is half filled or completely filled, it attains stability. So now nitrogen has attained the stability. But oxygen, if you see, there is no stability because it is not half filled or completely filled. It is partially filled. That means nitrogen is more stable than oxygen. That's why nitrogen is having more ionization enthalpy. It is very difficult to remove an electron. Why? It is now they are half filled, so they have attained the stability. The stability means very difficult to remove an electron. So you are getting why nitrogen is having more electron ionization enthalpy than oxygen. You got the point? Yes. Then next is down the groove. What's happened? Okay, next, see, there are various types of ionization, like ionization enthalpy 1, ip1, ip2. We call ionization enthalpy, as well as this is ionization potential. Ionization potential, that is ip. So if you have to remove one electron, then that is ip1. If you have to remove two electrons, then that is ip2, second ionization potential or second ionization enthalpy. Then ip3 or ie3, the same thing. So there is another question that will be asked. I'll take one question, okay? So question is oxygen and fluorine. Then ip2 of oxygen and ip2 of fluorine, which is greater? Because if you see first ionization enthalpy, fluorine is having more ionization enthalpy, first ip1 than oxygen, obviously. But if you think about the second ionization enthalpy, we may, I will like say, okay, first, if first is greater than, then second must be greater than, we may say like that. But there is some another thing. Yeah. If when we remove one electron, how many remains? 6. Then here, if you remove one electron, remains 5 electrons. See, 5 electrons means 2s2, 2p3. Now oxygen has attained the stable structure. You can see in the nitrogen, like nitrogen structure. That's why in this situation, oxygen is having ionization that will be more than fluorine. You got this point? Clear? So this is situation. Then trained. Next is down the groove. What happens down the groove? Down the groove. So down the groove, size is increasing. Size is increasing because shells are increasing. The electron is going farther and farther and far. So far electron means it is very easy to remove. So down the groove, what happens? Down the groove, ionization enthalpy or ionization potential decreases. There is one example. I'll tell this example and we'll stop. This last example. So this is nucleus and some shells are there. Yeah, and here is one electron. Okay, here is one electron. Then here is one another electron. Then this shell, and then this shell. So this consider this plus or the nucleus is like a parent. So the student is living outside. Okay. Oh, like see in India, if the students are from Mumbai, Pune, and the student is living in Kota. So the student is living Kota means far away from the parents. So parents does not have much control over the student. So if someone comes from outside, this the friend comes and he says, "So can we go for the movie?" Then the friend he will think for a moment and he'll say, "Yes, we'll go for the movie." Joy, yeah. So what he'll do? He'll be ready for going movie. Why? Because he has he is away from the parents, and the parents does not have much control over him. That's why he goes. So this friend needs very less energy. He just said, "Can we go for the movie?" And that person was very much ready. Yeah, we'll go. He said, "In fact, I'll pay the ticket." Then that means energy, less energy needed. Then say this electron is living nearby places. So other friend comes and says, "Come for the movie." He said, "No, parents will come to meet. Maybe some relatives will be there." So he is little afraid of it. So that's why he is little like he will not be able, like he said, he will say, "Okay, I'll not come." So you need come one day we can take the holiday, one day we can take the holiday, we can go, that is refreshment, so many things. So he may be ready after some like energy. Then this needs more energy, and this is living in the same city and this is living in the home. He must be attending, the online lectures from like ask guardians, and he must be in the home and parents are there. If someone calls come for the movie, he will say, "Oh, I can't come because I am staying in the home. I can't even leave for, okay, I can't even say, okay, I have tuitions outside." No, because you are in online. That is, it is very difficult to remove an electron when that is present in first shape. Means as we are going near and near to the nucleus, it is becoming difficult to remove an electron. You're getting my point? Yeah. So this is ionization enthalpy decreases. Then some effects. So ionization, the factors on which ionization enthalpy depends. So first is, we can say, the radius, the atomic radius, and then this is very important effect in nuclear charge, that is Z effect. So what is Z effect? Z effect is Z minus sigma. So this sigma is a screening constant. Screening constant. So what is screening constant? Screening constant or shielding effect. Shielding, screening effect or shielding effect. So what is shielding effect or screening effect? Shielding effect means, like I'll tell one example because we have so many examples in so many chapters. We are, because when we tell the example, that time you will not forget, because when I say the when I tell the example, you will not forget this concept the whole of your life. Okay, so this is very nice example. See, this is board and the teacher is teaching here. So this is he's writing something, or he's teaching something. So yeah. So here is the benches and the students are sitting, and see what is happening. One, two boys or some boys are sitting here on these benches, and there are some boys. Yes. So this whole class is filled. So those who are sitting front on the front bench, they are what they are doing. They're actually they are like the whole concentration of teachers goes onto them. They are just pulling, or we can say they are just pulling the concentration of teachers over them. They are just telling like this. I'm here, I'm here, I'm here. So electrons, those who are present in the first shell, they are telling like they are doing like that. They are doing this to the nucleus. Nucleus is seeing where is the electrons. Hey, this last orbit electron, where are you? And this first shell, second shell electron, they are doing like this. And they are what they are doing? They are providing the shield. They are screening the electrons which were present in the which are present in the last orbit. They are shielding. So that is shielding effect. So what is happening? These electrons or these students are providing shield. So if teacher, the control of teachers on these two boys is very less. There is doer and some fellow come, and he says, hey boys, come outside, we will play game. Then they will look upward, they will see, okay, teacher is not seeing us, and they'll just move outside. They'll just move outside. Why? Because teacher could not detect or could not see that particular students they were sitting. When they went, the teacher even could not understand, okay, someone might be sitting outside, or someone may be sitting in the last benches. Oh, he did not bother. Why? Because front benchers, they shielded the back benchers. They created the effect, and that's why we could remove, or they himself left. So same thing, if someone comes from this door and ask this student, can you come outside? Do you think they will come? They will go outside? No, because teacher is focusing. Yeah, the more focus, the teacher's focus is going on the front benches. So we can think, if electron is present on the last cell, shielding effect, because of shielding effect, the electron is very easy to remove. That means shielding effect is directly proportional to more shielding effect, less ionization enthalpy. Energy is required, less energy. So shielding effect is inversely proportional to IP. So more shielding effect, that means size is increased, and less energy required to remove an electron. Okay, and this is ionization enthalpy. There are more things, more exceptions, and things other that are like that we'll discuss in the next lecture. Okay, thank you very much.